Okay, so one of the things that I want to discuss is the relationship between potential and force. And so this is a pretty fundamental concept, okay, in physics and physical chemistry, and it's going to be pretty important. So there is a relationship between force and the potential energy. And one thing that you can think about is that the potential energy actually gives rise to a force experienced by the object, which is experiencing the potential. So, okay, mathematically, we can actually make the statement quantitative. We can say that the force is equal to the negative derivative of the potential with respect to space, okay? And so we're using, in all of these three potentials, we're using r as the variable to represent the spatial separation of our coordinates. So what we really mean in this case is that we want a derivative with respect to the variable r of our potential, where the potential is a function of r. Okay, so first thing that I want to justify to you is that this makes sense from the point of view of dimensional analysis. Okay, so is this statement dimensionally correct? Well, let's find out, okay? So first thing that I want to do for you is I want to remind you of two statements that we made before, right? So we looked at the dimensionality of force, right, where we said that we could take Newton's law, which is force is equal to mass times acceleration, and we could basically use that statement to figure out, well, what are the dimensions of force, okay? So the dimensions of mass are mass, which we denote with capital M, so that's m to the 1 for mass. And then acceleration, right, is equal to the change in position with respect to the change in time squared, right? So basically what it is, acceleration has dimensions of length to the 1 power times time to the minus 2 power, okay? All right, so this should be the dimensions of force. Mass to the 1, length to the 1, time to the negative 2, okay? Now, let's look at energy, and we used E equals mc squared to get at energy, right? Where again, we've got mass first. So in the first term, we have mass to the 1. And then c is the speed of light. And c squared is the speed of light squared. So the dimensionality of the speed of light squared is length squared over time squared. So overall, energy has dimensions mass to the 1, L to the 2, T to the minus 2. Okay? And so then we look at this statement, right, that we wrote here, where we said that, okay, let's take the potential, which is an energy, right? The potential has dimensions of energy, and let's take a derivative with respect to R, okay? And so then really basically what we have to figure out is, well, what is the dimensionality of this derivative with respect to R, okay? And it turns out that dr, okay, so the numerator has does not carry with it any particular dimensions. The denominator has dimensions of length, okay? And so what the dimensionality of this derivative operator is length to the minus 1, right? And let me just take a minute to sort of justify that statement as well. You know, if we wanted to take the derivative of the potential with respect to r, and we didn't know how to do, the math to actually find the derivative, we could use this idea that the derivative tells us about the slope, okay? And so what we could do is we could say, okay, well, the derivative with respect to r of v of r basically is approximately equal to v of r, some particular value of r, which I'm going to call r2, minus v at some other value of r, which I'm going to call r1, divided by r2 minus r1, okay? And then this is basically, right, this is a way of getting the slope, right? This is the rise of the function and divided by the run of the function, okay? So rise over run. And remember what we're doing here in the numerator is we're subtracting an energy from an energy. So that doesn't change the dimensions of the numerator. And in the denominator, we're subtracting a position from a position, or a length from a length. So that doesn't change the dimensionality of the denominator. So overall, I've got energy divided by length, okay? And so the dimensionality of energy divided by length, of course, from what we just set up here, must be mass to the 1, length to the 2, t to the minus 2, divided by length, which is overall going to be mass to the 1, length to the 1, t to the minus 2. And that's what we determined is the dimensions of force, okay? So this statement is correct. Okay, dimensionally, this makes sense. That's what we've shown here, is that taking the derivative with respect to a length variable of the potential could plausibly yield a force because the dimensionality is correct. Okay, now the other question is this negative sign. It helps to actually see some of these potentials before we make our assessment if our negative sign is correct. But at least at this point, what we've done is we've made an argument that the derivative with respect to a length variable of our potential should yield a force, because that makes dimensional sense.